So we'll talk about something else. SCC. What's SCC? What's SCC? Terminology. First session of graphs. So don't anyone remember SCC? Sorry, single. What Manan? What's SCC?
Don't know, bro.
Sam, do you remember SCC? Deva, Sam. No,
Single connected component, huh?
no one remembers.
No, strongly connected components.
Strongly connected
Okay,
component.
strongly.
And it only applies to which kind of graph? Directed or undirected?
I think directed.
Directed.
It said it applies only in directed graphs, because in directed graphs there is no concept of components. Okay, in directed graph it's all about the concept of strongly connected components. Okay, clear? So do you guys at least remember like, okay, let me ask you like this. So you have to tell me how many SCCs are there in this graph. Okay. Seven, 8. Chalo. Yeah. So how many SCCs? At least do you guys remember the definition?
I think every vertex need to be reached to another vertex.
Correct. So by coming with this definition, what do you think? I mean, how many SCCs?
In between there is a cycle. So we need to break between 4 and 1.
Nice, very nice. So can I say like all the pink colors are SCCs?
Yes, yes.
Correct, right? Because if you start anything from here, you will reach any node. Here also it's same. From 4, it's only till 4, 3, 5. Okay.
Can't we consider 4 and 3 as single component?
You can go from 4 to 3. What about 3 to 4? You cannot go, right?
Okay. Oh yeah.
Okay. So it's all about bidirectional. I mean, everything should be reachable from anywhere. Okay.
Okay.
Okay. So what we need to find is number of strongly connected components in a given graph. Okay? And there are basically 2 algorithms as mentioned in the starting. So what we will be looking is Kosaraju's. Manan, is he your friend? Kosaraju?
Yeah, my childhood friend.
Okay. There is another guy, I mean another algorithm, which is Tarjan's algorithm. Okay, so I am not okay, I am not using Tarjan's because I mean at least we will go through this, and I mean that's required for articulation points and all, but I'm not covering that. Okay. So we have to find number of SCCs. Okay, and so do you want me to take a interesting problem statement now, or shall we take it after completion of Kosaraju's? What do you say?
Anything is fine.
Others, what do you guys say? Shall we take a problem and see?
Problem?
Anything is okay, bro.
Okay. So let's take a very interesting problem. Okay. Now this time we all are playing together. Okay. We all are playing together, and we are in a magical city. Okay. We are in a magical city, and the right, there is a city, so obviously it has some kind of like paths. There are some uh, places, and you can go from here, somewhere, something. Okay. And since we are playing together, okay, and we can call any villagers over here. Okay. So I'm just doing some random large graph. That's all. So what we're doing is we are playing in a magical city, and somehow we got to know an information that today there will be a box of gold will be appearing in any of the node. Okay, node means, let's say, this is a entire, it is a very large city, and these are considered every node as a small cities or something as such. Okay, so we got to know that there will be a box of gold coming since it's a magical city. Okay, what you what we need to do is, it might come at any city. Okay, we are not aware of which city it might come in. Okay, we are not aware of which city it needs to come in. So what should be our main criteria? Our criteria should be, we should be able to cover all the cities. Okay, we should be able to cover all the cities. You need to tell, or we need to decide how many people we need to arrange such that we can cover all the cities, so that anywhere the gold box appears, we will be able to grab it. Is the story clear?
Yes, yes.
Manan, is the story clear?
A large city is there at any random.
Nice. I see. चलो. Yeah, a large city is there. कहीं ना कहीं सोना आने वाला है. ठीक है. That will be a gold.
Yes.
So what we need to do is, हम लोग को arrange करना है कि minimum number of people we need to arrange, so that wherever the gold appears, we should be able to catch. I mean, we should be able to grab that gold box.
Okay.
Number of components.
Hey, no, 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 it is not SCCs. It is not. It will help. It will take a help of SCC, but it's not number of SCCs. Okay.
Mhm.
Okay. Is the question clear, Deva Sam? Is the story clear, not a question?
Yeah.
Okay. चलो ठीक है. Okay, so first let's understand Kosarajus. Okay, what's Kosaraju? So you guys got to know, right? Like there are these strongly connected components and all stuff. Okay,
Mhm.
what we can do, there is a very famous technique, like which is required in higher rated questions, that you kind of compress you kind of compress. Okay, what's compress? This is, can you see, true 2 has been like 0 1 2 has been compressed to a single node. This entire thing has been compressed to a single node. Can you see this compression? This is known as compression. Okay, and now it's all about finding topological sort on this. So yeah, but we'll see this. I mean, there are some weak terms coming in, but at least can you see what do you mean by compression? Compression is a strongly connected component is becoming a single node. Now is it clear that compression means? What does compression?
Yes, but why not one like
Yeah, okay,
came?
okay. So this is some X. Okay, I mean I just wrote like 2, but
Okay, okay.
some random uh, int, what we say, identifier. Okay, not exactly node 2. Okay, something random X.
And
Yeah.
also why 5 came to 3?
What I'm saying is, this is a random identifier I gave. I mean, uh, this is 4, right? So I am saying
Yes.
this is 0. This might be 1. This might be 2. This is a compressed graph. Don't think as these numbers. This is, think it as, this is a single. So any, how we represent a graph, just a normal node, right, with some identifier. That's all. Don't think 4
Mm.
means it has to be 4
Mm.
over here. Okay, it's not like that. It is something. Okay.
Okay. Okay.
Okay. So now we kind of have to do a DFS for sure, okay? But what we need? So can you see, like, if we do a DFS from any order, we will not get our strongly connected components. Say I started DFS with node 1. What happens? Node 1 will be explode, node 2 will be explode, node 0 will be explode, node 6 will be explode, node 7, node 10, node 8, right? So if you start from any random node, can you distinguish between strongly connected components? You just went into a DFS, right? And you would never know 6 belongs to which component, 0 belongs to which component. Correct? Is the problem clear? I mean, what are we facing if we do a DFS from any random node? Quick yes if you understand, otherwise let me know.
Oh, yeah.
Others?
Yeah. Yes.
Sam, didn't you
Yes,
understand?
bro.
Okay. So you understood, right, what the problem is? If you start from any arbitrary random node, it's kind of difficult to identify, correct? But let's say I have done a DFS from 5 first.
Mm.
I'm just randomly saying you, okay, if I do a DFS at 5, if I do a DFS at this part, if I do a DFS at uh, maybe at 1, maybe at 3, and then maybe at 4, then are we getting it? Then are we able to differentiate now? Because from any SCC we are not able to reach to any other SCC. If I have done a DFS in this manner, can I say I am not able to reach to any SCC? Can I say that? Hana bolo bhai. Is, isn't it clear? I don't think of
Yeah.
how we will do it. I'm just saying you, if we do in this order, are you guys able to see that we are not able to reach to any other SCCs?
Correct. Yes.
Correct, right? So we kind of need this kind of ordering, right? So if we do this kind of ordering, probably we can find कि भाई कौन सा node in which SCC it is available, right? So if you see the decomposition or the compression of this, if I do like this, can I say I'm done? मतलब first do this, then do this, then do this, then do this, and then do this, then we are done. क्योंकि इस पे तुम करोगे कभी भी, what is this? This is a single connected component, right? And can you see that you are able to reach from here to here, but can you reach from here to here? Is there a way to reach here to here? No, right? Because there is no
Mm.
No.
edge. So if you start from this component, okay, if you start from any of the components here, the problem is you are able to go to this component, right? But we don't want to do that. We want to do in a reverse way. That is, if you start from this 5, there is no way to reach here, okay? So we kind of need to find out ki bhai, which node or which component to start from, which compressed component to start from, so that we will not go to any other one, okay? So what Kosaraju came up with is, he kind of taught two techniques, okay? One is store, okay? Store out time of every node. I will tell you what this is. And second is reverse the graph, okay? Store out time of every node. Second is reverse the graph, okay? So what do you mean by storing the out time? So do you guys remember this is the DFS function we used to write for neighbors if it is not visited? Do you guys remember this code?
Yeah, basic DFS.
Basic DFS, right?
Yeah.
So
Yes.
when we start a node, okay, v of some n equals to true, I'm making it true. This is known as entry time. Okay? Remember this, it will also come in handy in our last session of month 3. Okay. This is known as entry time. this is known as exit time. Entry means when you're starting the DFS, exit means when you're ending the DFS. Okay, so after all the nodes are explored, then only can I say my DFS is done for that node, because we will iterate on each of the neighbors, right? So out time is nothing but when the DFS of that node is being finished. Okay, that is something as out time. Clear? Out time is this. This is in time.
Okay.
Okay, so what Kosaraju asked is, since we are kind of not aware, okay, what he is saying is, see, if we start a DFS from 3, we are able to reach to 5, right? We are able to reach to 5. If we start a DFS from 5, we are not able to reach to 2, correct? So how to make sure that
Mm.
we have this condition? Can I just reverse the edges, all the edges?
Mm.
If I reverse all the edges, okay, what happens? Think and let me know. If we reverse the edges, what happens? Chalo, theek hai. First, let's go through these points, okay, and then probably we'll try to understand intuition. It's little. I mean, at first time you will not understand the whole intuition. So if you understand the code also, it's fine, because even it took me good amount of time to understand what's happening. Okay, so maybe today we'll focus on the first, the clarity, and then we'll go to intuition. But anyway, so what he says is that, let's say what we do, we started DFS, right? We started DFS, correct? So say we do a DFS from 0. From 0, where will I go to? I will go to 1. From 1, I will go to 2. From 2, I will go to 5. So can I say from 5, I can never go anywhere? I mean, it's the end, right? From 5, I cannot go anywhere else.
Yeah,
Sorry,
yes, yes, return
uh,
like this.
is it not audible only for me or for others also? I mean, Sas?
Yeah, even I am getting some disturbance.
Okay. So, Sam, I did not understand what did you say, but okay. So
Okay, network issue.
yeah, yeah. So what I'm saying is, if let's say we will do a DFS from 0, what happens? It will go to 1, 1 goes to 2, 2 goes to 5. So from 5, can I say I don't have anything to go ahead? That means
Mm.
5 DFS is done. So do you remember the out time? So can I say 5 will be pushed first, because 5 ka kaam is done. I mean 5 is done, right? So 5 is done first. From 5, again we will come back to 2. Okay.
Mm.
From 2, can we go anywhere else?
No.
No. From 1, can we go anywhere else?
No. Zero.
From 0, you see that there now 1 has been explored. Now we need to explore this path, right? Which is
Yes.
6,
7, 8.
right? So since we have started from 0, we go to 6, we go to 7 and 8. So from 8, since we cannot go anywhere,
8. 7, 6.
okay,
0.
7, 6, yeah. Next we have 0, because 0 DFS is done. And once we are done, what we do, like if you remember, we write a for loop, right? If it is not
Mm.
ended, do a DFS. So 0 has been done, 1, 2. So we will start from DFS of 3, correct?
Mm.
So 3 say we cannot go anywhere. So it will be 3 and it will be 4. Okay. So can you see, this is the order of exiting, that is 5 will be exited first, then 2, then 1, right?
Yes.
Right.
Yes.
So the first step of Kosaraju is to build this. Okay.
Okay.
Now, what Kosaraju says is, okay, since we kind of like, uh, what we need is, we don't want to go from 2 to 5, right? Because if we go from 2 to 5, what happens? We are kind of violating that we cannot identify from let whether 2 and 5 are in the same components or not. Although you can see from the picture that 2 and 5 are on different components, but it's kind of difficult, right? So what Kosaraju says is reverse this entire graph, reverse the graph. Okay, so we need to redraw again because I need to show you how it is working. Okay, 4 3 1 2 0, 4 3 1. See, like getting the intuition for the first time, it's hard. Okay, so at least if you're clear for 50 to 60% also, for code, don't worry, you can, it's very easy, but intuition is little tough to understand at the first go. So, okay, this is the thing. And if you see, I am reversing all the edges. Okay, so 3 will point to 4, 1 will point to 4, correct? 3 will point to 4. Now, can you just tell this? 2 will point to 1, 1 will point to 0, right? 2 will point to 1, 1 will point to 0, 0 will point to 2. So what I have done is I have just reversing it. Okay, I am just reversing the graph. 0 to 6 hai, so which is nothing but, and we need to, we have a 2 to 5 also. Okay, and I just reversed this direction, and 6 to 7 we have 7 to 8. So correct, and this part is also being reversed. So did we form the entire reverse graph now?
Yes.
This is a
Yes.
reverse, we did just build it, right? Now let's do a DFS from end cycle. Okay,
Okay.
so पहले क्या 4, correct? So if you do a DFS from 4, can you see you are able to reach anywhere?
No.
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 And this is your,
One component.
we will go to 3. From 3 you are able to reach 4, but 4 is already been visited, right? In our DFS we will write a visited, right? So 4 has been
Hmm.
Yes.
next we do a DFS on 3. So 3 ka done, 3 will go to 4, but 4 is visited, so nothing else. So from 3 we can not go anywhere else. Next we have,
0.
we start with 0. Okay, 0, so if you see, I can go to 2, I can go to 1, and from 1 we can go to 4, but we cannot because 4 has been already visited. So can you see these parts are coming into a single SCC now?
Yes.
Yeah.
The reason it is happening because even if you reverse the graph, SCCs will always be at same, right? What do you mean by SCC? It means you can go from anywhere to anywhere. If you reverse also, you should be able to reach vice versa. So that's what
Yes.
Kosaraju came up with, that
Okay.
you reverse the entire graph because it won't affect your SCC. Okay. Now 0 has been done. What about 6? Let's start with 6. 6 में देखो, you can go to 8. 8 say you can go to 7. 7 say you can obviously go to 6, but again it has already been visited. So can I say this?
Yes.
No. What about 7? So can you see 7 has already been visited by SCC 4? So nothing to do. Correct? So did you get this? 7 already been marked as true, right?
Mm, yes. Yes.
What about 8?
8 marked.
Yes.
8 marked.
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 Marked. What about 5?
Marked.
Okay, so let's start a DFS.
Only 5.
And can you see we got 5 components?
Yeah.
So this is how the Kosaraju works. Okay, so The code is simple, although the intuition, like it comes with little bit of reading and practice, that we don't know where to start from, and there is a chance that you can actually, like, from one component you can reach to other component. So what he says is you reverse the entire graph. So if you reverse the entire graph, and if you start from the back means whichever has been ended last, then there is no way to reach to other component, right? So can you see that initially you were able to reach from 4 to somewhere, right? But now can you see that from 4 you were able to reach nowhere? I mean, there is no way, because all the edges has been reversed. So this is how the Kosarajus work. Okay. Okay. I know it's little tough to understand intuition, but it's at least 50% clear. I would be happy if you say 50% too.
Yes, bro.
Yes,
Like
understood.
intuition is even reversing also should be same, right?
Yes.
Th-
Correct.
that's the reason when both are not matching. Yes, yes.
Yeah. True. Manan, did you understand?
Yeah, I understood.
So shall we quickly write it?
Yes.
Sam? Sorry, Sas, what do you say?
Ye-
Yeah, bro.
Deva?
Yeah, bro.
Okay. Okay. So what information do we need? We need number of edges. It needs static. What do we need? M. So we need a adjacency graph, right?
Mm.
And we also need a reverse.
Mm.
Okay. We also need something as obviously a boolean visited is needed, right?
Mm.
What else?
To store the result.
Uh, yeah. So we will print it directly, okay, instead of storing.
Okay.
And we need out time, right? You remember out time?
Yes. Yes.
Okay. And sorry, not. We will take this. Okay. We will take this while. Okay. So we should kind of initialize also, right? And reverse is the reverse graph. I hope you guys understand that. Okay. And we have out time. And what we need, we kind of okay. So we are done with the initialization part. Now what we are doing is we are reading the edges. Okay. So right, we have two edges to read. There is a directed graph. Okay. So reverse dot, is it okay? See, adjacency में u to v, in reverse we will have from v to u. Make sense?
Yeah.
Does it make sense, guys? Adjacency पे u to v, reverse पे v to u.
Okay. Yeah.
Okay. So once this is done, what we need to do?
In directed, we write only U to V, na? नहीं.
Yeah, we wrote this only, right? U to V. We did not
हाँ.
write V to U. ये तो reverse वाला graph है. This is
अरे वो रिवर्स है. ओ सॉरी सॉरी. हाँ मैं रिवर्स नहीं देखा. सॉरी.
ठीक है. तो बुलियन बना दिए. अब पहला DFS कॉल कर देंगे. ठीक है. So if you remember, right, we do like this. Simple DFS. If DFS 0, okay, int node. So first thing first, for integer neighbors, adjacency dot get node. Okay, if it is not visited, what we need to do? And once DFS is done, do you remember what we would have done? Out time pay. What should I write here, Manan? Out time dot add.
Node.
Clear, right? So is everyone clear? What we have done in DFS, first DFS, went ahead,
Yes.
done a DFS, stored its out time.
Yeah.
Chalo. So once we are done, we will have something ready, right? So what we will do is we will reverse it. Why reverse? Because I mean we could have started from, like, we would start from here, right? So I'm just reversing it.
Yes.
That's all. Collections dot reverse. What is it?
Out time.
Out time. Okay. Collection dot reverse out time. We reverse that, and uh, since our visited will be filled, so what we need is arrays dot fill of. Okay, I am just filling, again making visited array as false. Okay, because with this DFS 0, what happened was everything was made it as true. So now since we need to do a DFS second time, I have made everything as false. Clear? अब क्या करना है? So we kind of need SCC, right? I mean, which component belongs to which SCC, correct? So starting int SCC number, static static component. SCC number, new int. Okay. ठीक है. So for integer in, now what should I write? Out time, right? Because we will iterate on out time now, correct? Now if visited of x, dfs2 of x, okay, and what we will do is we will increment component. Okay. Now why? Because every time whenever it is unvisited, you remember, right, we have a new component got formed.
Yeah.
Static void maybe dfs2 int node. Okay, first thing first. Okay, I can just, and what should be this, correct? For the
Yes.
second time we will iterate on reverse. Okay, and we will also store SCC number of this node is nothing but comp. Okay, and this should be clear.
Yes.
अब क्या करेंगे? For int I0 I less than I plus plus system dot println node I is on SCC Makes sense, right? We are just printing it to see which SCC it does belongs to. Okay. And I guess we are good. So did we forget to initialize anything? Because in case if we have not, we will get a null pointer exception. So I hope we have done everything. Okay. We should see in action. Okay. कौन सा graph लेते हैं? Shall we take this graph itself?
Yes.
So please try to. I mean, we need to take the original one. Obviously, this is the graph. 1, 2, 3, 4, 5, 6, 9 nodes. 9 nodes. How many edges? 1, 2, 3, 4, 5, 6,
10.
7, 8.
10.
10 or 11? But देखो 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, right?
10.
चलो ये वाला someone kind of remember this 4, 3, 4, 3, 4, 1, 3, 4, 1, and
1, 2, 2, 0,
yeah,
0, 1.
1, 2, 2, 0, 0, 1. 1, 2,
2, 0, 0, 1.
2,
2,
5,
5, 0, 6. 2, 5, 0, 6, 6, 7.
7, 8.
7, 7, 8, 8, 6. 7, 8, 8, 6.
चलो node okay, node 0, 1, 2 are on SCC3. Did you see this? 0, 1, 2 SCC3 में आया था.
Yes.
Node 4,
Yes.
node 4 is on SCC1. Okay. So 0, 1, 2 are on SCC3. Node 3, where is node 3? So did you see node 3 का SCC2 है? Right. Node 4 का 1 है. Node 5, you remember node 5? This is separate. So we got,
Yes.
and finally 6, 7 are. Makes sense?
Yes. Yes. Correct.
Okay. So this is what your Kosaraju's algorithm is. Okay. Now you kind of know that which node belongs to which component, and you can kind of manipulate based on the question. Okay. So we need one more thing, right? What's that? Compression. We need a compression. So compression we can, right? So how should we do compression? Can anyone say me how to do compression? Okay, so what I'm doing is I'm creating a new graph now, which is a compressed graph. Okay, so कितने रहेंगे? At max it can be only SCC component, number of SCC components. So I've initialized that to that many. Now for neighbors, adjacency dot get of I. Okay, if okay, so when we connect guys, let's say we are talking about this graph, right? So this graph has to become this graph, correct? True. This is a compressed graph, right? Now when we connect, whenever there is an SCC, whenever there is a different SCC numbers, we connect it. Do you guys agree with that point? क्योंकि
Yes.
when we connected, because they are having different, right? If SCC number of I is not equals to SCC number of neighbor,
Neighbor.
in that
Neighbor.
case, compressed graph dot get of SCC number of I dot add SCC क्या ये वाला and can I say this? देखो अच्छा से देखिए एक बार बोलो. If they are not in the same component, if they are, then only there should be an edge, right? Make sense?
Yes.
Right.
Okay.
Okay. Now we will print the compressed graph probably so that we have a little bit of good understanding. Okay. So for int I equals to 0, I less than how much? This I am writing only for the second time in my life. So that's the reason I'm a little kind of scared. Okay. So anyway, and correct तो होना ही चाहिए. System dot print. Should we have printed like this? For node, I don't know. 0 से आएगा कि 1 से आएगा, I'm not sure. Okay, let's just see. Maybe it's not a better way of printing. ठीक है. So compressed graph dot size, we just went off the road and we just kind of did this. Okay. Okay, so like for node 0, how to tell this? For node 4 we don't have anything, for node 5 we don't have anything. So do you remember what is the SCC of each one of them? इसका SCC क्या है? 4 का SCC? So 4 का SCC is 1, right?
1.
1. Node 3 का SCC क्या है?
1.
Node 3 का SCC is 2, right? Not
Yes.
2. Okay.
and this 120 has a SCC of 3, I believe, correct?
3.
Yes.
And finally we have node 6, 7, 8 is 4.
And left one is 5.
So left one is node 5 is having SCC of 5, correct? Can you see the graph which has to be formed is right? तो 1 से 2, 3 में रहना है.
Okay.
Okay, let me make a small change. Where it is? Yeah. ठीक है. Now you see it would be perfect. अब देखो node 0 node 0, there is no node 0, right? Because our numbers are starting from 1 now. Okay, can you see for 1, 2 and 3 are connected? Can you see for 3, 4 and 5 are connected? Are you seeing this now?
Yes.
You're getting a
Yes,
picture,
yes.
Yes.
right? So this is
Okay.
what a compressed graph is. Okay, now like there are some other algorithms which comes at the top of this. Okay, obviously अभी तो औकात से बाहर है, but uh, like you kind of compress this and you kind of do some manipulation on this. Okay, because now this is a graph readily available, right? And if we have a graph, you know that there are many data structures or many algorithms you can uh, apply upon this graph, correct? Compressed graph. So you can play with this now. Okay, so this is what I just wanted to show you, that this is a SCC ka part and this is a compressed graph. Okay, so now is it clear compressed graph kya hai?
Yes, bro.
Okay, now let's
Yes.
end
Yes.
our discussion with the last thing. So you have a graph, right? City. Still we are playing and we need to find gold wala.
Yes, bro.
Initial question.
Yeah,
So say,
magical one.
yeah, let's say something you have like this. Okay, right? Let's say some city. So what are the SCCs? Can I say uh, this is one SCC?
Yes.
Hmm.
Okay, इसका इधर है. Let's like this. Let's write it like this. Okay, and say like there is nothing as such. Okay, I mean I'm just drawing something. Okay, and what else we have? This is one more SCC. So this is one SCC, large SCC. This is one large SCC. Okay, so can you see like there is some reduced graph which is being formed now, right? There is some reduced graph which is being formed, correct? Now you know that anything within this is reachable, correct? Can you say that anything within this is reachable? Guys, hello? Anything within this SCC, I mean, this was some random graph, and assume that we have converted this graph into this converted form. Okay, assume that. Now you guys,
Okay, after compression.
yeah, after compression. Now you tell
Okay,
me uh, how many members are required.
two.
How to?
A number of separate components, right?
Uh, Not exactly like that. But if you see, see, this is a directed graph, right?
Hmm.
Okay. So can I say that if you make stand someone here, okay, let's say
Can reach to any point.
exactly. So in the final compressed graph, whichever the node is having in degree as 0, if you make
Hmm.
them stand here, can I say he can cover everything? Because if there is
Yes.
an edge, he will definitely go here and here, right? So somehow
Yes.
if we make this guy stand here, it can go to here and here and here. But let's say if you make him stand here, there is no way you can reach here. So you need one more person extra. But we need minimum number of people, right? So whatever the nodes are having in degree as 0, can I say that's the answer? तो क्या करेंगे
Yes,
स्कूल
bro.
में? We will go quickly. Okay, SCC number of neighbor plus plus, right? Because there is a direction being formed I mean, there is a graph being formed, right? And int minimum people 0. Okay, for something on this, you need to travel on this compressed graph. Okay, if in degree, oh, how can I use another arrangement? And what's that? Uh, we used one variable, right? SCC compo. Okay, so since we are doing an in degree, okay, SCC compo, I discuss if in degree of finally done, right? This is the one which we need,
Yes.
right? So finally go to everyone, जिसका भी in degree 0 है भाई कर दो, हो गया. Clear?
Yes, bro.
It's a hard level question, by the way. But obviously I have seen this solution, so okay, so this is it.